Okay, so thank you very much. So these participants of this meeting of the Biennial of the Spanish Royal Society of Physics, good morning. So my name is Javier Junquera, professor in condensed matter physics at the University of Cantabria here in Spain. And it's a big pleasure and an honor to present Professor Sayeeff Salahuddin. Professor Salahuddin is the TSMC Distinguished Professor of Electrical Engineering and Computer Science at the University of California, Berkeley. His group explores physics for low-power electronic and spintronic devices. He's mostly known for the discovery of the negative capacitance effect that shows a substantial promise for logic memory and energy storage devices. Professor Salahuddin received the Presidential Early Career Award for Scientists and Engineers, the highest honor awarded to early career scientists in the United States from President Obama. Salahuddin also received several awards, including the National Science Foundation Career Award, the IEEE Nanotechnology Early Career Award, the Young Investigator Awards from the Air Force Office of Scientific Research and the Army Research Office. Additionally, this year, indeed, in 2024, in recognition of his contributions to negative capacitance and its recent adoption in integrated circuit devices, Salahuddin received the IEEE Andrew Grove Award, widely known as the highest award given by IEEE for device physics and material research. Previously, in 2019, he also received the IEEE George Smith Award. Professor Salahuddin is a co-director of the Berkeley Device Modeling Center and Berkeley Center for Negative Capacitance Transistors. He has helped organize multiple initiatives within the CHIPS Act in the United States and is currently an executive committee member of the Northwest Artificial Intelligence Hardware Hub with the Microelectronic Commons. He currently serves as the editor-in-chief of the IEEE Electron Devices Letters, which is the premier journal of electronic device research. Professor Salahuddin is a fellow of the IEEE, the APS, and the American Association for the Advancement of Science. So it's our pleasure to receive Professor Salahuddin. So now the crown is yours.
Thank you, Javier, for that very generous introduction. And thank you very much for inviting me and giving me this opportunity to talk here today. This is a wonderful place, my first time in San Sebastian, and I had no idea how beautiful this place is. So again, thank you very much for making this happen for me to come here for this. So what I'm going to talk about today is functional materials for energy efficient electronics. Let's All right, so let's start with this recognition that information processing, the way we see it today, it impacts all layers of our lives, all right? So often when we think about information processing or computing, we think about computers with a keyboard, with a screen and all of that. But underneath, it is actually impacting every layer of our life, starting from computing, the traditional computing work, to drug discovery. The way we figured out the vaccine for the pandemic in a very, very rapid time was enabled by a lot of computing. In the US, at least, that I know about, food distribution is heavily dependent on computing. If the computing network breaks down, food distribution system in the US will break down. So if you actually think about that, computing permeates every layer of human life, and its impact in our life is going up every year. However, computing, although we seem to take it for granted, is not free, okay? So what this plot shows is world compute performance in zeta instructions per second. And that's, this is in year, this is in the block plot. So, so basically the number of instructions that we are running is going up exponentially every year. And every instruction that we run is associated with some energy. So if we look at that energy, that is going up like this. I mean, of course, this is also going up exponentially. So the thing to see here is that the rate of increase in the energy that is required to do computing is actually much faster than how the world energy production is going up. And it is projected that by 2034-35, these are dashed lines because this part is projected up to this much. We have kind of data because we know the kind of machines that are going to come out in the next 4 or 5 years. It is projected by the mid of the next decade, we will actually be spending single-digit percentage of world's energy for computing. Right, that is a humongous number if you think about it. And more importantly, the rate of increase is much faster than world's energy production. So essentially, this is not a sustainable trend. In fact, this has been recognized a long time ago, and in the way we design our computers already takes care of this. We do all kinds of designs to make sure that we reduce the energy dissipation as much as possible. Some of you may remember, in 2003, 2004, actually 2004 when I started doing my PhD, I could buy a computer with a clock speed of 5 gigahertz. Today, for you to find a computer that runs at 5 gigahertz will be very, very hard. Most of our computers are running 2.3, that also at turbo mode. Most of the time your laptops are running at maybe 600 megahertz because we need to reduce the amount of energy that we are spending. But usually we don't think about it. The first time, at least in my view, people thought about the energy dissipation in computing when the Bitcoin mining became very popular. How many of you know about Bitcoin mining? Many of you. How many of you have actually done Bitcoin mining? None. I don't know, maybe in the Europe it was not as popular, but in the US, even my grad students were setting up servers to mine Bitcoins. But what happened, the reason that Bitcoin mining by rank and file actually went away, only big corporations now do it, is because at some point, as the Bitcoin coin mining became harder and harder, at some point the electricity bill that you had to pay to mine the coins was higher than how much coin you could actually mine from that computing. So that was the first time I think that, rank and file, like us, we kind of figured out that there is a energy price to pay for computing. Otherwise, we don't really think about it. However, there is an energy price, and this trend is not sustainable. So as I said that in computing, in the system design and others, people have already been, for the last 10 years, they have been doing all kinds of stuff to reduce the energy dissipation as much as possible. We, of course, work on the materials and device and physics side. So our goal is to work on the fundamental building blocks of computing and try to see if we can bring in energy efficiency there. And that's what will be the main focus of my talk today. But before that, I will... Okay, that works, so I'll try that. All right, so just to do justice to my title, In the pursuit for improving energy efficiency, what we have been advocating for is this vision for CMOS+X. So we are basically saying that silicon CMOS has been there for many decades, and it keeps improving. And we, in electronic side, there is this myth that silicon is dying. When I came to do my PhD 20 years ago, I heard silicon is dying. My advisor told me that when he came to do PhD 20 years before that, he also heard that silicon is dying. But silicon actually never dies, because I think that the reason is that thousands of very smart engineers continuously work to improve it. So silicon keeps improving, and I think we can kind of, if you have to bet your money, you'd say, no, silicon is going to improve. But the point is that we can bring in functional augmentation to the conventional silicon CMOS, and that's what I call CMOS+X. So we will talk about a functional augmentation that at least my group has been working on for quite some time now. Yeah, that works. All right, so the main physics principle that we like to work on is this collective order for energy efficiency, and I'll try to explain what I mean. So a lot of our work in my group goes on the ferroelectric materials. A ferroelectric materials is an insulator where the centrosymmetric metal atom is slightly off-centered. That gives you a permanent dipole. But if you can imagine that you have a lattice, okay. Oh, that was, you know your technology. Yeah, so if you think about a lattice with permanent dipoles have electric fields that come out of there. So these unit cells where the electric fields are coming out, they will see each other just through very classical dipolar interaction. But that dipolar interaction itself creates a collective order in a ferroelectric material, in the sense that all these electric fields work together to polarize the material in one direction. And that then stores some energy inside the material. Now, if we look at thermodynamics, what it says is that if we want to transition from one state to the other in an isothermal process, then the total energy dissipation, and we are interested in energy dissipation because we want to improve energy efficiency, is the change in the free energy, which is kT log of W, where W is the degree of freedom. So just from here, you can see that if I can use a system where the degrees of freedom is limited, a reduced order system, then to make the transition, I need smaller energy. So that gives credence to this idea that if I can use the collective order to actually make transitions, then I will thermodynamically spend lower energy compared to a completely non-interacting system. And all our switches, all our transistors, all our memory devices, everything is a transition between two states. We go from state 0 to state 1 or vice versa. So back in 2007, we basically said that we need to look into these materials with collective order for computing, because it seems to promise that I will require lower energy for transition. Okay? Now, for ferroelectric materials, this collective order gives me some stored energy, and it tries to polarize the material. But if the material is polarizing, remember that the centrosymmetric atom is trying to go in one direction. It is off-centered. So if it is continuously polarizing, the material is kind of going up like this, right? And due to Hooke's law, it will try to become skinnier and taller. But if it keeps going, at some point it will explode, which will be a fantastic phenomenon, but nature does not allow that. So as it tries to go up like this, the spring energy of the system brings it back. And so there is a balance. So there is a spring energy in the system, and so there is a balance point which gives the material the lowest energy, and that's where the material is stable. Now, if you look at this energy landscape, what you can see is that in the middle part of this energy landscape, I can fit an inverted parabola, which means that if I am writing an equation, U equals to Q square over twice C, the C must be negative. It's an inverted parabola. It's a maxima of a curve, so the second derivative is going to be negative. And that means that in this region, the capacitance is negative. And remember that this is the region where collective order dominates. So if I want to take advantage of that thermodynamic advantage of energy efficiency, I have to work in this negative capacitance region. So that's what I mean when I say negative capacitance. This is what I mean. However, I also want to point out that the material is not stable here because this is not the minimum energy point of the material. So material is stable there, where the collective order has been balanced by the spring energy, so I cannot actually expect to get any advantage thermodynamically. So I have to do something to push the material in a region where the collective order dominates. So I was here or there, and I need to do something so that it goes there. And so what we said that there should be a simple way of making that happen. Energy is a scalar. So if I put some positive energy in the system, let's say I put another dielectric which has a parabolic energy landscape, just Q square over twice C, then I'm adding this W of a ferroelectric with this parabola of a dielectric. And if my addition is appropriate, I will get this green curve. That is the composite energy landscape. And for this composite energy landscape, the minimum energy point is actually here. Okay, so locally, the ferroelectric is sitting in a region where the collective energy dominates and my capacitance is negative. Locally, right? It's not globally. Globally, the material is still in its minimum energy position. But locally, the ferroelectric has to go there to minimize the overall energy in the system. So that was a very simple way of trying to push the material in this region where it by itself doesn't want to go. Okay. So if I do that, what happens? If I look at this composite energy landscape, I can see that to switch the same amount of charge, x-axis is charge, I need a smaller amount of energy compared to my dielectric, right? And so if I look at the U equals to Q square over twice C, this means that for the same charge, if energy is lowered, my capacitance has gone up. Now, this is not surprising because, again, thermodynamics told us that to switch for the transition in this collective order-dominated region, I would need a smaller energy. So that's what I'm seeing here in the energy landscape is just basically the manifestation of that thermodynamic principle. Now, if you're an electrical engineer, you often like resistances and capacitances. So from capacitance point of view, it is a very interesting construct because what textbook tells us is that when we put two capacitors like this, one on top of the other, the total thickness has gone up, capacitance must go down. That's the textbook description of capacitance. Here, I put two capacitors on top of each other, and I actually see a capacitance going up, not going down. So it goes exactly in the opposite direction of what the textbook says. Now, capacitance going up also means that I can switch the same amount of charge at a smaller voltage because capacitance is dq dV. So high capacitance means I switch the same amount of charge at a smaller voltage, and that essentially means that any device that works within the principle of a capacitance, I can switch it with a smaller voltage. And the device that we all know that works within the principle of a capacitance is transistor. Okay, so if I can switch the same amount of charge at a smaller voltage, I can get to the on current at a smaller voltage. That will reduce the voltage requirement in all our computers, And our computers, the power dissipation is CV squared. So if V goes down, the power will go down in a quadratic manner. So this can help us fundamentally reduce the energy dissipation in the basic building block itself. So that's the pursuit that we had. And it was kind of quite exciting in the sense that field effect transistors, they're called field effect transistors because of the field effect. And we are kind of aiming to change the field effect in the field effect transistor, right? So the basic field effect can be changed if we can make this happen. So these are all principles, and so we need to look into real experiments. Does this happen, right? So the first experiment that we started looking at is this capacitance increase, because again, this is exactly in the opposite direction of what textbook says. You put two capacitors in series, capacitance should go down. That's what textbook says, but in this case, the capacitance should go up. So our first experiment came out in 2011, and where we actually put this strontium titanate, that is a dielectric, and on top we put a PZT, and we actually saw that the capacitance is going up in these systems, showing that the ferroelectric is working like a negative capacitance in this system. In this paper, we talked about something that I will read because it will become important in a few minutes. So we said that the enhancement in capacitance can be useful for ultra-dense dynamic random access memory, that's the DRAM applications. Increased capacitance beyond the classical limit can also lead to novel supercapacitor structures for energy storage. So, but let's focus on the capacitance enhancement right now. So a few years later, we actually said that it may be advantageous to, rather than doing just one ferroelectric dielectric, rather than doing that, let's do a superlattice. And there's no theoretical reason really for it. There is an experimental reason to do it. And let me try to explain that. As just an experimentalist intuition, which is the fact that you want to push the material here where the charge is almost zero in the ferroelectric material, right? And when you try to do that, in a system like this, the charge has to be zero everywhere in the ferroelectric material, because if you have a little bit of charge left, the metal does not allow you to have a lateral electric field. So the metal brings in some kind of a pathological condition for the material, for an experimentalist, because that means that your material has to be exactly uniform everywhere within your experimental domain, which is very hard to do. So what we said that we can kind of, math remains the same, but experimentally, if we just put a dielectric here, then I give the ferroelectric a little bit of more freedom to, kind of break into domains and give me a net charge equals to zero, because now there can be lateral electric field in these boundaries. So when we did the superlattice actually showed us the capacitance enhancement, and at that point, around 2014-15, there were many other groups around the world with different combinations of ferroelectric dielectric also saw capacitance enhancement. So that gave us confidence that what we are seeing is not just in our lab. It's actually quite robust. All right. So in that continuation, one of the experiments that I thought at that point when we did this experiment that this will be my end with a negative capacitance is an atomistic imaging of the effect. So this is a superlattice. This is STO, lead titanate ferroelectric and STO. And here, this is done with my colleague at that time, Ramesh Ramamurthy, whose group actually grew these materials. And what we could do is that by looking at, in the TEM, we could actually map out the polarization in this system. So you can see the polarization unit cell by unit cell here, because you are looking at the deflections unit of the atoms unit cell by unit cell. And of course, from a macroscopic measurement, the capacitance enhancement was present. By that time, we could measure capacitance enhancement in many different combinations. So this was not a surprise. But we now knew that how the polarization looks like inside when the capacitance enhancement is seen outside. Okay? But what we could also do with David Muller's group in Cornell is to map out the electric field in the system. So the way they do it is that if there is an internal electric field in a material, you send in an electron beam, it gets deflected. So by using a very, very sensitive detector, they can then say how the electric field looks like inside the material. Again, these are very, very recent developments and very exciting, because we used to say built-in electric field you cannot measure, but actually people can image it now. So we now know the polarization and we now know the electric field locally, and so we can figure out the flux density directly, epsilon naught E plus P. We have measured E and P both, and we can then calculate the G in the system, and we can see locally that we have this higher energy regions. We often call this suppressed polarization or frustrated polarization regions, where the second derivative is definitely less than 0. So we can actually atomistically image this local negative capacitance region, and you can see that they align up very well where the polarization actually goes to 0 in this material. So we, in fact, could both image and calculate a negative capacitance in the material and then measure macroscopically the capacitance enhancement. And this is a work that was also done in collaboration with Javier, who did a fantastic second principles calculations, and very, very rigorous. He spent some time at Berkeley as well. I remember very interesting discussions with Javier, where he will tell me that, Sayeeff, delta P over delta X is not the same as delta X over delta P inverse. Because, so we went through all these very intense discussions, but in the end, the experimental results and simulation results actually agreed quite well, and that gave us a lot of insight to perform our next set of experiments, where I'm going to go next. But with this, with the atomistic imaging of the negative capacitance, I kind of felt that, okay, physics-wise, what I wanted to see, we have seen it, right? So, okay, that's it. But at that point, also, around the same time, there was also this thing, and in fact, I was told this back in 2015-16 when we started getting all these results, is that, okay, Sayeeff, these are okay, nice experimental results, but you won't be able to impact electronics in any way by doing this, because of the fact that perovskites are not compatible with silicon in terms of their growth. We are, of course, doing perovskites in our lab in epitaxial substrates. The other thing, which is more fundamental, at least that's how it looked like at that time, is in the 100 years history of perovskite ferroelectricity, we know that when we reduce the thickness of the perovskites due to the size effect, due to the depolarization field that comes in, perovskites become very weak in ferroelectricity, and at some point, actually, for most perovskites, the ferroelectricity goes away below 5 nanometers. On the other hand, if you look at our advanced devices, even in 2018, the FinFETs, the fin pitch, the distance between two fins was only 43 nanometers. Today, it is only 29 nanometers. That is 58 silicon atoms. And that has to contain your gate oxide, gate metal, then other things. So right now, the gate oxide in our transistors is only 1.8 nanometer thick. So I was basically said that, I was basically told that, if you lose ferroelectricity below 5 nanometers, there's no way you can use it for electronics, because the advanced devices need 1.8 nanometers. As you go farther, you will need even less. So we started then looking at this problem, and we kind of said that, okay, people know about perovskites very well. How can we engineer that system? Rather, we started looking at hafnium dioxide-based ferroelectricity that was discovered at NAM lab in Germany, where they showed that a polycrystalline hafnium dioxide material grown in low temperature actually shows ferroelectricity. And it's a new material system, so we thought that there are new opportunities there. And that kind of, I'm not going into the details of this work, but that kind of worked out very well. We actually saw that hafnium dioxide-based materials, even down to 1 nanometers, this TEM is for a 2 nanometer film, is actually robustly ferroelectric. So that was very interesting. And what we actually saw is that in these films, as we thin down the material, the distortion in the lattice goes up. So it becomes even a stronger ferroelectric as we thin it down. So following the same path, we saw that undoped zirconium dioxide, so just pure zirconium dioxide, when we thin it down to 1 nanometer or so, becomes ferroelectric. And just for the fun of it, we went down to close to 0.5 nanometers, which is 1 unit cell for zirconium oxide. And 1 unit cell of zirconium oxide is also ferroelectric. So this showed us that there is no thickness limit with these kind of systems in terms of ferroelectricity. So we can go back and start engineering the energy landscapes again and try to get the functional augmentation that we have seen in perovskites. So, this is back in 2018, we started making transistors because these hafnium zirconium oxide is compatible with silicon, so we could immediately go and start making transistors. And we started seeing what we projected. We, if you remember a few minutes ago, I said that a negative capacitance effect is supposed to steepen the curve like this, the IV curve, and that's what we started seeing in the actual transistors. These were planar transistors. We also then went to FinFETs, and I know I'm not going into the details of it, but basically we saw the effects that will come for capacitance enhancement in FinFETs as well. Around the same time, Global Foundries, this is a big semiconductor manufacturer. They did an experiment by putting in a ferroelectric in their process, and they also saw the capacitance enhancement related effects in their transistors. So that was very interesting. But these were all, basically go and try. And but we wanted to do a little bit better than that. And so we came back to what our learning was in the perovskite-based systems. So in the perovskite-based systems, what we learned is that this superlattice, remember, allows the ferroelectric to break into domains. And in the suppressed polarization regions, we see very large negative capacitance. So what we started doing is we started making superlattice-like structures with hafnium zirconium. So the particular superlattice I'm showing here is a 4 angstrom hafnium dioxide, 12 angstrom zirconium oxide, and 4 angstrom hafnium. So this is really, in my mind, an atomic engineering. You are really going by unit cell here, right? And if you then look at the synchrotron XRD, you see both tetragonal and orthorhombic phase stabilized side by side here. Tetragonal is a non-polar phase, orthorhombic is a polar phase. So basically these materials are breaking into, kind of a polar, non-polar, polar, non-polar, very much like the perovskite superlattice that we have seen there. And then this is what we saw. So I will spend a minute to explain what we do. So in semiconductor literature, capacitance is often explained or quantified with a parameter called effective oxide thickness. So it's nothing but the inverse of the capacitance normalized to silicon dioxide's capacitance. Okay, so if your effective oxide thickness is larger, then your capacitance is lower. Your capacitance is higher, means EOT, effective oxide thickness, is lower. So usually what we have is we have silicon, then we have an 8 angstrom SiO2 in our advanced transistors, the transistors that you are using in your computers. And then, as I said, that we usually have a 1.8 nanometer hafnium dioxide. So typically what we get is EOT is 8 angstrom from SiO2 plus something from the dielectric. That's what we get. But what we saw is this is Intel's advanced transistors. EOT is 9.5 angstrom. Our transistors had an EOT of 6.5 angstrom. So you see that EOT has gone down. So capacitance is up, that you can see from here. But very interestingly, the EOT is smaller than the thickness of the SiO2, which means that for our high K, the effective oxide thickness is negative. And that is happening because the ferroelectric is providing some kind of a negative capacitance in the entire stack. And so with that, we could then build transistors. I will not spend too much time here, rather here as to where we are today. So we, at Berkeley today, we can make around 30 nanometer channel length transistors, 30. So it's not very small, it's 30, but it's still not very large. Now, if you compare that with TSMC's 30 nanometer transistors, as you probably know that TSMC is the world's largest manufacturer of transistors, you can see that at the same voltage, I have higher on current and lower off current. That is compared to a commercially available transistor that we use today. And the reason that I can do this at the university is because of that capacitance boost. Capacitance boost means that at the same voltage I get more charge. More charge means that if the electrons are flowing in the same velocity, I will get more current. So my charge boost is so high that even without the bells and whistles that a commercial foundry has, I can actually beat them in our transistors. And I want to mention that this is no projection. This is directly measured data, data versus data. There's nothing else here. If I actually normalize it to their kind of source drain resistance and others, this advantage will be even higher. Okay? So one of the things that we often talk about, and in ferroelectricity people have often worried about, is the speed. Is the speed a problem? So we usually look at 40 gigahertz radio frequency transistors to measure the speed and measure what is often in engineering we call the transconductance, which is a quantity that is a product of capacitance and velocity. And you can see that again, compared to commercial transistors at the same channel length, our capacitance times velocity is way larger. That's because our capacitance is very large. So this is important because often people would worry that if you are changing the gate oxide, the electron velocity in your silicon channel may be affected. So you need to look at the product of both. And what we see is that the electron velocity in our channel is not affected. All right. So just to also mention that this is not only limited to our lab, many other labs have now reproduced it, but more importantly, recently, we have now transferred the process to MIT Lincoln Lab, which is a fab for US defense that does technology transfer for US defense. We had a defense program within which we actually transferred our process to their fab, and they get exactly the same results that we get. So we are very happy about it, that it's completely reproducible and transferable technology. It's not something that is a one-off experiment. All right, so now I think I'm coming close to my allotted time. So I'll mention something. Remember that in the beginning of my talk, after our first experimental demonstration of the capacitance enhancement, we said that, yes, we are very interested to look into transistors, but the capacitance enhancement helps other things like energy storage, like a large capacitance that we need in the back end of our processors, and like DRAM, where you are storing your memory in a capacitor. So what happened is in 2020, we saw an announcement from Intel, which says they're introducing super MIM capacitors, and it said that thin layers of different high-K materials, each just a few angstrom thick, stacked in a repeating superlattice. So when we saw the announcement, we thought, it looks very similar to what we say. But we, of course, did not know what that is. But in 2023, Semiconductor Digest published a report from ChipWorks. So if you don't know, ChipWorks is a company which does reverse engineering of products. So they actually break down products and they see what is inside. So it took 3 years for them to know what is in there. but what we found is it is actually hafnium zirconium oxide and hafnium aluminum oxide. And the interesting thing is that you are trying to increase capacitance. You know, zirconium oxide has a much higher permittivity than hafnium. So if you wanted to increase capacitance, you will never introduce hafnium in there. They were previously using just zirconium oxide. Now they have introduced a lower permittivity material to increase capacitance, which makes no sense. But it actually makes sense if you think that this is a ferroelectric material increasing the capacitance there. At the same time, actually, that 2020 was an interesting year in the sense that last year, through Tech Insights or ChipWorks reverse engineering work, we also got to see that Samsung DRAM it has now introduced an hafnium oxide in their zirconium oxide material. So they're also using it, this capacitance enhancement, to actually scale down their DRAM. So it took, let's say, since 2008 was the first time we talked about negative capacitance. Took around 12, 13 years, but it's very happy thing to see that actually it's being now used. And in fact, if you have bought a Samsung phone after 2021 or a MacBook Pro, which uses Samsung's DRAM, then you are using that in your gadgets. So that's a good kind of adaptation into integrated circuit devices. So this is my last slide. So most of our journey through materials engineering and looking at the physics and trying to make it work for capacitance enhancement, we have mostly looked at transistor type applications. But if capacitance is going up, of course, you can use it for energy storage as well. So as things started to go into technology, we started looking at energy storage. And in a very recent work, we have seen that actually energy storage can be quite high. So if you look at this x-axis, this is the energy storage, and it is this solid state superlattice negative capacitance material stack has very similar energy storage compared to standard micro supercapacitors that we use, which is based on very, very complex materials and cannot be really integrated onto our chips. So from that point of view, the energy storage is quite high, but because this is a solid state capacitor, it can be charged and discharged extremely fast, right? It mostly dependent on what is your power delivery capacity, because energy over time is power, and so you need tremendous amount of power to charge and discharge it very fast. But otherwise, you are just charging and discharging a capacitor. It can be extremely fast. So what we saw is that the power density is almost 5 orders of magnitude larger compared to what the standard supercapacitors that we have seen. So we think that this could be a completely new direction to use this, what I often call the dielectric response of a ferroelectric for energy storage. All right. So basically, what I wanted to present today is that we think that there is much opportunity to actually bring in functional augmentation to CMOS. If you think about negative capacitance, it is mostly a functional augmentation. I'm bringing in a functional augmentation, but that can significantly contribute to the energy efficiency. Again, larger capacitance, as I described, that simply means that you can switch the same amount of charge at a much smaller voltage. And negative capacitance allows you to do that at a voltage that is not accessible in a conventional way. So, so this is just one example, but there are many different ideas that are out there in photonics, in MEMS, in optics that could probably bring in other functional augmentation that can improve energy efficiency significantly. But I think to make this vision successful, we need people from many different disciplines to come and work together, because it is very difficult for one person to know everything that is happening. And so I hope that as we go forward, as our systems become complex and more and more complex, this is what is going to happen, is that we from various disciplines will work together to bring our computing to a sustainable trend in terms of energy. So on that point, let me stop. Thank you.
So we are ready to take questions now. There's one here.
Thank you very much. If I understood correctly, when you go to these very thin layers of half a nanometer, that wouldn't work, because there you will not have the domains. You need to go to the superlattice to have these domains. Because actually I'm having problem to see how the domains will be in such a narrow, I mean, will be lateral domains, which is what you have actually. But
yes, it will be. It will be lateral domains. In fact, it's a very good question. So the question is that in a let's say 1 unit cell ferroelectric, how can I sustain domains? And it will be lateral domains. We have been able to image them now. We can see the domains. It will be lateral domains. But for the effect that we are looking at, we do want the lateral domains because it is inside the domain wall where the polarization is suppressed, and we see the capacitance boost.
what will happen if you reduce also these dimensions?
If you reduce the if you reduce the lateral size as well, we don't know what's going to happen. We only have data up to 80 nanometers on the lateral size. Below that, we don't know. It's an uncharted territory for us. Yeah.
If I may, a very short question too. You mentioned the transconductance, and this is mobility and capacitance. There are independent measurements of the mobility. I see that your measurements are showing that the velocity is not decreasing, but is the independent measurements of the mobility is not affected by all these?
Yeah, it's not. We of course did those independent measurements of mobility, and the it is not affected. Maybe, I don't know. I kind of did not go through that slide. So this is a mobility measurement, for example. So we can, it does not really change, and it's not very surprising because what we know is that it is the SiO2 layer that is on top of silicon that dominates everything, and we are not touching that. We are putting everything on top, and so, yeah.
Any more very short question?
We are not very big in patenting. We kind of do open source and let people use that.
So thanks for the nice talk. In fact, it is not a short question, I think, or it is maybe a short question, but maybe the answer is not short. So here you have shown this thing of the landscape of to have negative capacitance and so on. But basically, after you speak about domains and the formation of domains, and this is a manifestation of the effect of the polarization field and so on. And in fact, there is not a direct relation between this landscape and this formation of domains and so on. No? And in fact, there is a paper from David Jimenez, I think, and Andres Cano. They spot these things not very clearly. I think it's a very interesting work, not because they are from Spain. It's a very nice work. And I am asking myself, so the results are clear and all the things is spectacular, but what is the contribution, or what can be the contribution of this enhanced domain wall mobility, for instance, or this contribution of having more domains or more effect of the polarization field without a pure intrinsic negative capacitance effect to show this kind of increased capacitance effects, and also the thing of the higher on-off, no, higher on-off, no, the higher SS parameter in the transistors?
Thank you for that question. So I think, let me see if I can quickly go there. Yeah, so I'd say that how the domains play a role and how do we think about energy landscape when the material is breaking into many domains was the question that we were trying to study in this experiment. In the sense that it is actually inside the domain wall where the polarization is suppressed. So that's suppression is what I want, because when the polarization is suppressed, that is when you are accessing the stored energy in the system. And if I have two domains and the polarization is going like this from up to down, it is in the middle where it is suppressed, held by the two domains. So if you first asked me that, what do you want in terms of the maximum negative capacitance? I want many domain walls. I want a small domains because the domains don't give me too much. But I want the domain walls where the polarization is suppressed. It's very similar to the frustrated spin lattice that we think about in terms of spin. The polarization is frustrated because of the electrostatics that is outside. Now, how that is connected to energy landscape is also kind of we learned from this experiment in the sense that we can then look at the energy landscape locally. And locally, you see that I will see this kind of, peaks and troughs. And the peaks is where the energy is stored and polarization is suppressed. And then it will look like a, double well-shaped energy landscape, but there are many of them locally kind of stabilized. So it's not one. Now, if you are very pure, if you're looking at very pure physics, you'd say, I don't want to define that. I want to define one energy landscape for the entire system. That is a very different thing, right? But if you are looking at locally, you can still use that concept that I have a stored energy, and so that second derivative is becoming negative. That's how, at least I think about this.
Thank you.
Thank you very much. Yeah, really appreciate it.
Good morning, dear college. I'm Paz Garcia Martinez. I'm Professor of Optics and President of the Specialized Group of Women in Physics. It's my immense honor to introduce today a truly remarkable woman who has made significant contribution to both the field of optics and fight for women scientists' rights. We all have to congratulate for having among us Professor Ursula Keller. She's a renowned scientist whose groundbreaking research has greatly advanced our understanding of ultra-fast lasers. As she said in some plenary talks, I just want to do good science for the love of lasers. And I think that if lasers could have spoken, they would also have been able to express their love to Professor Keller. In fact, Ursula Keller has patented several relevant inventions in the field of ultra-fast lasers for industrials and medical application, and she also applied these lasers to conduct a second experiment testing fundamental processes in quantum mechanics. She's the creator of the atom clock, one of the most accurate time measurements devices in the world, which can record time intervals up to few attoseconds. Her amazing career started after graduating in physics engineering in 1984 from the Swiss Federal Institute of Technology in Zurich. She continued her studying at Stanford University, where she obtained a master's degree in applied physics, and then continued with a doctorate in physics obtained 2 years later. After that, she joined AT&T Bell Laboratories as member of the technical staff, where she conducted research on photonic switching, ultrafast laser technology, and semiconductor spectroscopy, and developed a method for manufacturing ultra-short pulse lasers. Since 1993, is a tenured physics professor at ETH Zúrich, directed the molecular ultrafast science and technology from 2010 to 2022. Her awards include the Swiss Science Prize Medal, Benoist OSA Medal, SPIE Gold Medal, IEEE Edison Medal, among many other medals and awards. Keller has supervised 94 PhD students, authored more than 500 journal articles, and she has over 55,000 citations. In addition, Professor Keller pioneering fundamental actions to promote women in science, because women, as everybody knows, persist underrepresented in science and in particular in physics. And progress towards equal representation of women remains slow. Professor Keller created the Women Professor Forum in ETH Zúrich as the former director. She is an active and brave defender of improving work culture for women with better governance, with better transparency in decision-making and access to resource and privilege. She's truly an inspiration to all of us, and we did thank her visit to our biennial meeting. Today, she will share her insights and experience in dual-com generation from a single laser cavity. So thank you very much, Ursula Keller. The floor is yours.
Okay. Hello, everybody, and I'm very grateful for this very generous, overwhelming introduction. But it's true, we have to introduce women properly. Thank you very much. And I hope you will stay also for the women panel later on, because I think in the physics community, we can only change the culture if my male colleagues contribute and jump in and help and try to understand what is going on. So, but before we do this, I would like to do this physics talk. And it's a part of laser work in ultrafast short pulse generation, which has been going on in my life for more than 30 years. And this is something that we got into it, and I'm really excited about it, and we also started a company, another company based on this. So I really think it will revolutionize spectroscopy and ultrafast measurements. So whenever you want to do an ultrafast measurement, you can actually use this novel laser technology. And let me explain that a little bit more. So the outline of my talk will be first to explain a little bit how ultrafast and frequency metrology came together. What is a dual-comb laser? And why is this actually interesting for many applications? And how do we generate these two combs out of the same laser? So you've been probably aware of this frequency metrology revolution, because it received a lot of attention recently. And originally, you know, frequency is the most accurate observable that we can measure. And, you know, for many, many years, the microwave clocks have been dominating the field. And based on the microwave clocks, we also have really high quality GPS, right? But then the optical clocks came along, and a key invention that is this optical frequency comb was driving this optical clock down in better and better action. So it's the fractional frequency uncertainty with higher and higher accuracy, really fast, and is now driving the world record. We are now in the fractional frequency precision of 10 to minus 18. And when you think what that means, it's basically moving the clock by 1 centimeter along the direction of the gravity. You can measure the change in time based on the general relativity theory. So if Einstein wouldn't have done the work, we would have discovered it now, or with a GPS anyway. So, but this opens, of course, a whole bunch of very interesting applications, and some, you know, we can define the second much more accurately, because, you know, the higher the frequency of oscillation, you count the oscillation, the more accurate the second is defined. There's a whole bunch of application. One of the ones of my favorite is probably if we ever gonna be able to measure if the fundamental constants in our physics law are actually constant, and that would really change physics quite a bit if we would be able to measure that. At the same time, to this frequency metrology revolution, we also had a revolution in ultrafast lasers. So this is over the similar time scale. You know, we reached shorter and shorter pulse duration, first using dye lasers, getting down to 27 femtosecond, getting compressed to the few cycle regime. And then the breakthrough came with the Ti-sapphire laser, which was was developed and discovered by Peter Moulton in 1982, and it became commercially available right when I graduated with my PhD. So material, you know, as we have seen in the previous talk, material matters, and that was really making my career. Because within a very short time, we reached new world records in terms of pulse duration directly out of the laser, and we reached then a level of a few cycles, because at 800 nanometer, the optical cycle is 2.7 femtosecond, and we cannot get much shorter than an optical cycle because the spectrum has to be positive and DC doesn't propagate. But what was also different going to the solid state system is that the noise of these pulses were so much better, and that actually made a change for the frequency metrology. Basically, what comes out of a mode-locked laser is are pulses given by the round-trip time of the pulse within the laser cavity. And, you know, mode locking has been around for a long time and has been described theoretically for a long time by Sigmund Haus. And it always described mode locking with the pulse envelope, you know, so that after one round trip, the pulse envelope needs to be the same. But there is also the electric field underneath the pulse envelope. And as we approach this few cycle regime, we actually had a new problem, because the question was, what actually happens with this electric field underneath this pulse envelope? And because when you understand the mode locking, it is always the pulse envelope after one round trip. But the electric field underneath this pulse envelope is subject to random fluctuations. And the question, we actually had a Gordon conference in nonlinear optics in 1995, where we had this discussion, and we considered this the holy grail problem, how to actually measure the position of the electric field underneath the pulse envelope and how to ultimately stabilize this. And we called it the carrier envelope offset phase, obviously, because, you know, you have the electric field, which is the carrier, and you have the pulse envelope, so it's the carrier envelope offset phase here. So when you have a phase that changes with time, then you can take the derivative and you get a frequency. The question is, what frequency is that? And you can actually show with one line of simple math that this offset of this, that this frequency is actually the offset of this mode-locked pulse train in the frequency domain, which is a frequency COM, and the offset is given by this position. And once you understand that, you can come up with a whole bunch of ways how to stabilize this. And so we learned over time to not only stabilize the spacing of this mode-locked pulse train, but then also the offset. And with this, we had basically a frequency comb with a very high precision. And when you have a frequency comb, you can measure an unknown optical frequency with very high precision, because all you have to do is take this optical frequency, measure it with a normal waves, which gives you a few digits of the frequency, but then to get these 18 digits afterwards, you actually translate these unknown digits into the microwave domain with the beat signal, which is only at maximum half of the pulse repetition rate of these lasers. So you translate an optical frequency in the hundreds of terahertz into the 100 megahertz, gigahertz, which you can count. And this digit accuracy is by counting cycles. And at this frequency, you can count cycles, and this is how you get the frequency precision. So this definitely changed things, you know, in this field. But now, what is a dual comb? Why do we need two combs? So a dual comb laser is a laser that can generate not only one comb, but actually two combs. And these two combs have the same spectral information, but have a different pulse repetition rate. So when you look in the time domain, you have the two pulse trains. They have different pulse repetition rate. So it's only a small change. You know, normally the laser maybe is at 100 megahertz, and the difference is a megahertz or less. And if you fully transform this pulse train, you get this frequency comb with different spacing. So we came up with very simple ways of creating these dual comb lasers. And it's actually funny how it goes with inventions. And when you realize how to do it, you think, duh, why did nobody else come up with this idea? But the beauty is in the simplicity. Okay, and I will explain then afterwards a little bit more in details how these lasers work. But first, I want to tell you a little bit why this is so exciting. There are a number of review articles having come up during the COVID time. You know, some people wrote textbooks, other people wrote review articles, so COVID time was a little bit time to think. And I just want to mention these two review articles because they give the most references in terms of applications and ideas why this is really a cool technology. So the ability to stabilize the full frequency comb, both the spacing and the offset, would allow to do these dual comb laser applications by just simply taking two mode-locked lasers and stabilizing all the three parameters. The repetition rate stabilization is pretty simple, but the offset stabilization is a little bit more complicated. And so this requires quite some sophisticated feedback loops. It can be done, but this, of course, adding complexity and expense to applications, and you need two mode-locked lasers. So by actually doing everything in one laser, you benefit from the shared cavity configuration, so it has much higher stability, and you can actually get, for most applications, you don't need to do any stabilization at all. And so you have to ask yourself, if you ever want to buy a mode-locked laser again, why should you buy a mode-locked laser with only one comb when you can get two? Okay, and that's really what I try to convince you. And you can always switch one off, so why not buy two? Okay. So why is it so exciting? Why do we care? Let me explain this with the pump probe measurement. Ultra-fast measurements with short pulsed laser is based on pump and probe, right? So you come in with a pump, you change something, and then you come with your probe at a certain time delay. But now you can use one comb, for example, as the pump and the other comb as the probe. They have different pulse repetition rates. So when you look initially at time 0, the pump and the probe arrive at the same time, but then because of the different pulse repetition rate, the probe will be a little bit delayed with regards to the pump. So when you, for example, measure ultra-fast response, like, for example, a saturable absorber on a mirror, the reflectivity goes up because with the pump you bleach the absorber, so the reflectivity goes up, and then it recovers in pico, femto, and so on, time constant, and you would like to measure that. So with your probe, you come and measure this reflectivity, but always at a little bit time delay. And you translate this real time into an equivalent time, and that's why it's also called equivalent time sampling. So the real time window, when you look at it as the pulse repetition rate, is in the nanoseconds for 100, or 10 nanosecond regime for 100 megahertz laser. And if you then adjust the difference in the pulse repetition rate, the delta F rep, you then reduce this time window to 1 over the delta F reps to 0.25 microsecond. So you can scale the real-time axis to an equivalent time axis, which is then in the time domain that you can see it on a scope. So the whole ultrafast measurement is reduced to a scope measurement, right? And equivalent time sampling, this is not a new idea. It actually goes back to microwave technology. And it has been originally the first time applied by my PhD advisor for electro-optic sampling, okay? And so this is just showing you an example of a measurement of cesium reflectivity. Here, this signal is a nonlinear frequency mixing of the pump and the probe, so that only gives you a signal when the two pulses overlap, so this is time 0. And then we just increase the pump power and do this pump probe measurement, and you can see that we get this fast response in equivalent time as if it is an electronic measurement, but you can do it on a femto, on an attosecond time scale, and see it on a scope, right, on the microsecond time scale. This is really changing how you make ultrafast measurements. So any pump probe you can translate into this equivalent time sampling. So one really interesting application of this is for dual-com picosecond ultrasonics, because when you look at the whole industry of the electronic devices, you have a whole bunch of layers of thin films which you would like to characterize without destroying the sample, right? And one method to do that is with picosecond ultrasonics. So this goes back to the 80s and has been really commercialized to look at multi-layer stacks in CMOS technology to characterize the thin film layers. And the advantage is that when you do it with acoustics, it is you can go through non-transparent material. So it can be metals or whatever, because you use the pump here to produce an acoustic wave of in the material. The acoustic wave will propagate through this layer stack, and at any point where you have an impedance change, you have a partial reflection, which ultimately come here, which you then probe again with the second pulse. So so you see here then the reflectivity change in your probe laser as the acoustic wave comes to the surface again. And the signal that comes at a certain time delay is very small. So you need signal to noise of 10 to minus 5, 10 to minus 6. But the nice thing about using acoustic waves is that the speed of sound is, of course, much slower. It's 5 nanometer per picosecond. So with 100 femtosecond pulse, you can actually get angstrom resolution on the thickness layer of these multi-layer stacks. So if you have, for example, a 100 megahertz laser, you have a scan range before the next pump pulse comes again of 10 nanosecond, which lets you look at these multi-layer stacks of 25 micrometer with really high accuracy. So there is a huge interest in this picosecond ultrasonics in the semiconductor industry for non-destructive testing of these layer stacks. And we just saw examples before. So this is, for example, a test where we got a test sample with a commercial provider, which are doing this type of measurement, but still with mechanical delay lines. And so we did this measurement on a thin layer on silicon wafer, and you can see, boom, there is the fluctuations. You right away get the thickness out of these materials. So, what else? Spectroscopy. Spectroscopy, Fourier transform spectroscopy, I believe that all of you know what this is. Conventional Fourier transform spectroscopy is you put a light here into a Michelson interferometer, and you delay one arm, and what you measure then is an interferogram as a function of this displacement. If you then Fourier transform this one, you get actually the spectrum of the incoming light of this in this application. So if you put an absorber into this arm, you then change a little bit the interferogram that you measure, and if you then Fourier transform this, you get the absorption line. And the line width, the accuracy of your measurement, it depends how long you can make this displacement. So the longer you make it, the more accurate are these lines in the measurement. So it takes time, right? So you can do this with this dual comb as well. So if you have two combs with different repetition rate, and you send one through the absorbing sample and the other one, when you bring both onto the photodetector, in the frequency domain, you can look at it. Here are the optical combs. One comb sees the absorption, the other comb doesn't, and then in the microwave, the beat signal between these two combs on the photodetector gives you the microwave comb given at a spacing of the delta F rate, and you can see the absorption in the microwave comb directly. So this is how you look at it in the frequency domain, but you can also look at it in the time domain. In the time domain, the analogy to this displacement comes because the two pulses come with different repetition rate onto the photodetector, and when they overlap in time, they create this interferogram, now as a function of time instead of displacement, right? And when you then measure this interferogram, it's repeated every 1 over delta F rep. So if you then measure this interferogram and you Fourier transform this, then you get the microwave comb. So it's important that you keep this in mind. This is the notation I will keep using during this talk. You have the pulse train Fourier transform, you get the optical frequency combs. If you put it on the detector and you measure this interferogram and you Fourier transform this, you get into the microwave comb. The microwave comb is easily measurable with the electronic instrument. So, this is how we then measured the first time with a free running laser, water absorption, and we sent both of the combs through the water absorption. So, and measured the interferogram, and we used a reference and measured the interferogram, and then in the time domain, each interferogram took only 0.25 microseconds to measure, and then it averaged over time. And then if you Fourier transform these interferograms, you nicely see then the absorption line on the frequency comb by eye, and you look at the difference, and that's how you do the measurement. And because this was done with a free running laser with no stabilization, we convinced the editors in Science that this is really a paradigm shift for this type of applications. So this shows you also, for example, a similar measurement with the terahertz spectroscopy. So you use one comb to create a terahertz signal, then let it propagate in air, and use the other comb to then sample the incoming comb, so the interferogram of this signal, and as a function of time, and then you average it over many, many interferograms. And then, you know, if you take the time window as large as possible, you get a nice, good resolution here in the terahertz spectrum. And for example, with this measurement, which took an integration time of 2 seconds, integrating you know, over 40,000 interferogram. For example, we got a 55 dB dynamic range and 2 gigahertz resolution at around up to 3 terahertz. And of course, if you would make this time window longer and longer, then your resolution becomes larger. You see here that we have a little bit a spurious signal. This is not something unexplained, because it just shows you that then the terahertz signal gets reflected and comes back and gives you another nice interferogram. So this shows you an actual measurement, again, on the, it's a pump probe experiment, but now on the scope, because the measurement takes not much time. And then we put, for example, a sapphire window into the beam, and then you see how it changes. So this is kind of how fast you get ultra-fast measurements done. Okay. So how do we generate these two comms out of a mode-locked laser with a single laser cavity? Oops, sometimes it doesn't want. So as I pointed out, is we actually, it's very simple, it's embarrassing simply, but these are the best inventions, in my opinion. We just add a birefringent crystal into the laser cavity. Or we put a spatial multiplexing. So instead of a flat mirror in the laser cavity, we just put a little bit of a, close to flat, but a little bit of a biprism here, either in reflection or in transmission. And we change a little bit the path lengths inside the laser cavity. And with this, we change it by, you know, megahertz or kilohertz in the repetition rate. And with this, we get two mode-locked laser out of it. So initially, we demonstrated that with an optically pumped semiconductor laser, because it's really simple, and that actually triggered this idea. Instead of having an ion-doped solid-state laser like a terbium-doped or Ti-sapphire laser, it is actually an optically pumped semiconductor laser. So you have here a quantum well-gain structure, air-coated, and then going to the output coupler. And with this optical pumping, you can scale the power of these lasers by simply changing the mode size, because, you know, the gain chip here is only around 10 micrometer thick. And so if you open up the mode size to larger, you have like a one-dimensional heat flow, and you can effectively take the heat out of this laser. And that's why this is also called a semiconductor disk laser, because, you know, the active region is so thin. So with this kind of lasers, this laser has been actually commercialized, so it's not just an academic dumb idea, you know, optically pumping of semiconductor lasers. No, this kind of lasers have been commercialized by Coherent, and the external cavity here is the semiconductor chip. It's a V-shaped laser cavity, because they also want to have the option of adding a nonlinear crystal into the cavity to extend the wavelength range of operation. This type of laser has replaced the Ti-sapphire laser for biomedical application, because it's cheaper to just buy a whole bunch of these lasers than to buy a Ti-sapphire laser and to get exactly the wavelengths you want for your application, because with bandgap engineering, you get exactly the wavelengths you want, and you're not stuck with what you get with ion-doped solid-state lasers. And that's why it's such a powerful system. So this is a recent review article by Mirza, you know, shows you the average output power that has been produced from these optically pumped semiconductor lasers using indium gallium arsenide laser materials. You know, over 100 watt of average output power has been demonstrated out of these lasers. And as you know, I'm in the business of mode locking. So I invented this CSEM device, which solved the Q-switching problem in ion-doped solid-state lasers, which is a semiconductor Satur absorber on top of a Bragg reflector. Now, this optically pumped thin disk laser, or the VCSEL, is also a semiconductor. It's a bottom high reflecting mirror, a gain region, multiple quantum well, and then an air coating. So normally, when we did the first passive mode locking of these lasers, we just used it as a V-shaped cavity with the CSEM as the Satur absorber and then the VCSEL as the gain chip, and successfully mode locked this laser. But then, of course, because both is semiconductor, sometimes it really doesn't want to go, huh? Either the battery is low or this thing. Tech support, can you get me the next? I'm really pressing hard, and it doesn't come anymore. Great. Okay, so you can integrate this into one wafer stack, with the gain quantum well here and the Satur absorber here, and then you put an additional DBR which reflects the pump light so it doesn't start to saturate the absorber. You put that, next slide, next point. Yeah, you put that in an extern in this linear cavity, right? You pump it, and if everything is set correctly, you get a mode-locked pulse train. And at 3 gigahertz, you need a cavity length of about 5 centimeters. So this is not something you very easily integrate on a chip. And that's why, and a lot of the dual-com application actually work in this few gigahertz regime where other laser technology and COM technology has a hard time to get stable COMs at these lower frequencies. Next. So, as I said, this mixel, you just pump this mixel chip, then, you get your mode-locked pulse train. And if you then add, next slide, add a birefringent crystal, and you just pump 2 spots on the mixel chip, you then get 2 mode-locked pulse trains with different polarization, because one polarization that is also a stable solution of this linear cavity is the extraordinary beam that goes a little bit of a different path through the birefringent crystal and therefore has a different path length. So, simple physics integrated into this device produces your dual-com laser. Next slide. And with this, we demonstrated the first time this free-running spectroscopy measurement. But of course, the spectroscopy measurements are more interested in the longer wavelength regime. So, so for example, this shows you in the short-wave infrared regime, where you have the fingerprints of all the relevant gases, trace gases. And so we received then an ERC grant to push this technology into the longer wavelength regime. Next slide. So all the previous work I did in the gallium arsenide, aluminum arsenide, indium gallium arsenide system, and to push it to the longer wavelengths, we had to change over to the gallium antimony system. We had to develop the whole characterization, the whole CSEM, next slide, the whole, characterization, the CSEM, the VCSEL, and ultimately the mixel demonstration, all in this material system. And for this, we just needed the money to actually do it. Next slide. And when you look at the prior work before we started it, there was actually some really nice work by the Fraunhofer group where they did CW operation of gallium antimony-based VCSELs, optically pumped, and they could demonstrate up to 17 watt of CW output power at room temperature. And if you compare this technology to other like QCLs and so on, you see that this power performance of these lasers are very competitive and very attractive. But of course, the Fraunhofer group did not do the mode locking. So next slide. That was actually our job. And over time, we then successfully demonstrated also the mixel in the gallium antimonide system operating at a center wavelength of 2 micron. So you have an AR-coated section, then you have like 15 indium gallium antimonide quantum wells, then a pump DBR, and then an indium gallium antimonide absorber layer here. And this is then on top of a high reflecting laser wavelengths, right? And as you can see, the field enhancement is a little bit higher in the absorber than in the gain. It is because in the semiconductor you have so-called dynamic gain saturation, which you don't have in solid-state lasers. So from pulse to pulse at steady state, you have significant gain saturation. So you have to make sure that the saturable absorber saturates before the gain to open up the net gain window that supports your stable pulse generation. You don't want to make it too resonant, otherwise the whole system becomes very tricky to work. And something you also want, you want a rather fast saturable absorber, which we could get with this indium gallium antimonide saturable absorber. And there's a whole bunch of really interesting physics only on this absorber, which we have been able to characterize. Next slide. So we then did the mode locking out of this laser with 27 milliwatt output power, you know, for spectroscopy application, that's plenty. And the repetition rate in the gigahertz with picosecond pulses. And then, next slide, we added here a spatial multiplexer, basically a nearly flat calcium fluoride window, but it has a little bit an inverted biprism here, which is only 30 degrees, but this basically makes the laser cavity, linear laser cavity, then stable for 2 beams with slightly different path lengths. And with this, we obtained then a dual-com mode-locked mixel. Next. And you can see, because, you know, the separation of the 2 beams on the mixel chip is like 2-3 millimeters. So the uniformity of the chip in this university MBE system is not perfect, but still we had significant spectral overlap of the mode-locked pulse train, and we could actually then use this laser, next slide, to do a first demonstration of absorption measurement of CO2 around 2 micrometer. And the measurement, again, is done extremely fast because we adjusted the delta F rep to 2 megahertz. So the key is really to do the measurement fast. So this just tells you that the technology is there. You can dial in the wavelengths with bandgap engineering based on the semiconductor lasers, but to commercialize this requires a little bit more investment. So we started a company, but not based on these optically pumped semiconductor lasers, because we want to first establish the market and really show that people are interested to buy this kind of laser, and actually doing it with diode-pumped solid-state lasers, because we've started many companies based on ultra-fast diode-pumped solid-state laser. We know how to do this. And so this is basically the K2 photonics that we started. So K is not, we love mountains in Switzerland. K2 is obviously a mountain, but it's also because COM in German is COM, and so COM2 is basically the name of the company. Next slide. So this is now based on these diode-pumped solid-state lasers. So it's ytterbium-doped solid-state lasers. And when we did it with this spatial multiplexing, where this biprism has only 1 degree, but it changes a little bit the path length inside the laser cavity, we built an 80 megahertz laser cavity, sub 140 femtosecond. In each COM, we had 2.4 watt of average power, so plenty of power. And the RIN, the relative intensity noise, is in each COM is extremely low, and the relative timing jitter is 2.2 femtosecond. Actually, the noise was so low that we had to come up with new measurement, next slide, system, which is referenced in this one, and if you're interested, because any COM technology could actually use this technique, because the problem that we are having right now is that people don't use consistent noise characterization and, and say whatever, but at the end you need to measure it and give the proper data to show that what the COM technology really works. And so this shows you the laser cavity of this 80 megahertz cavity. So you have basically a gain material here. It's a terbium-doped solid-state laser, an output coupler, and you pump 2 spots here separated in the gain, and because you replace a flat mirror here by this biprism, you then have also 2 spots on the sesum, and you have different path lengths. Both of the combs are nicely, stably mode-locked, soliton mode-locked. Next slide. And you get your nice, here spectral overlap perfect, because of course it's terbium doped equal everywhere inside the crystal. And what you can also tune, next, you can tune the difference in the pulse repetition rate. And next slide, let me explain that. That's also very simple and it's useful for many measurements. So by just, so by simply translating this flat, nearly flat mirror laterally, you change the difference in the path lengths of the 2 combs. And next. And that gives you then the tuning of the delta F rep between, for example, in this cavity, between 450 hertz to 600 hertz. So this is also very useful for many measurements that you actually can change it. And then for many applications, you would like to have a higher repetition rate. 1 gigahertz is actually a sweet spot for many applications. And then, the spatial multiplexing doesn't work so well in reflection to get 2 separate beams in the gain and 2 separate beams on the sesum. So you can use it in transmission. And the biprism, so it's in the other direction. You don't see the 2 beams otherwise. And then, with this ytterbium Calgo laser, we then demonstrated next 3 watt of average power with 78 femtosecond at 105 micrometer at 1 gigahertz. And you can then, again, by translating this biprism, you can tune it. So these are powerful, ultra-stable frequency comb. And why do we care about going up to a little bit higher repetition rate? Let me remind you again how the measurement is done for example, for the spectroscopy. You're looking at the microwave comb. The spacing of the microwave comb is given by the delta F rep. The delta F rep is also determining how fast you make the measurement, how fast you measure the interferogram. So when you look at the microwave spectrum analyzer and you have here the 2 pulse repetition rate of 1 gigahertz, and the small variation between the 2, the microwave comb shows up around DC and around the first harmonic. And if you want to make the measurement fast, the microwave comb becomes wider and wider, right? But if they start to overlap, then you have aliasing, and you need to prevent aliasing. So if you want to have a wide optical spectrum and you want to make a measurement fast, you want to choose the pulse repetition rate as high as possible. Okay, next one. So now, if you make a measurement fast, it is also low noise. And so this shows you, without going into the details, but the key is really understanding noise in these lasers, this shows you the timing jitter of these lasers, and you can see there is a lot of low frequency noise. This is how much it fluctuates in the arrival time, because this was an open system, but both combs share the same noise. And so when you look at the frequency on the delta F rep, the uncorrelated noise is strongly reduced. And if you make a measurement, only the noise above the delta F rep is relevant. So the higher you move this one up, the lower is the noise in your measurement, and that's why it works, right? And so you have, so you normally, for every application, you try to get up to the repetition rate, choose delta F rep as fast as possible, and you don't need any stabilization, because next slide, and do again, click. So this is a measurement of such an open laser. Directly on the scope, you see the microwave COM here, and the Fourier, or the interferogram and the Fourier transform, whatever, you know. So this is the microwave COM, and this is the interferogram, and you can see over this long time, as we are watching it, it's drifting. But as long as you can actually watch it here on the scope, drifting not too much, you can actually track it and do the averaging. This is called coherent averaging, and let me jump over because I'm running out of time. Next slide. You can actually then determine how to track it. It becomes all a computer program done very fast, and you can then integrate this interferogram even over seconds to get a higher signal to noise. Okay, and the key is, you know, in these free running lasers, when you look at the interferogram, you've seen how this interferogram has been moving around because, you know, we are not stabilizing the laser. So initially, this moving is very little. That's why you want to make a measurement fast. But if you then integrate, this moving goes a lot, many, many rats. And if you look at the derivative of this phase, you know, it goes, but you can track it. And the key is that the second derivative is less than pi. And as long as you can, if you have that, you can track it and you can measure it, and you can actually, in principle, average as long as you want, you know. So it works. And it tested, next slide, next. And it is tested with a beat signal that this is really working. Okay, let's go next. Running out of time. So I just showed you a number of applications, but of course we've done it with many more applications, which also have gone out to other people. And in principle, you can buy now these lasers, for example, also for precision laser ranging, where you have sub-wavelength accuracy over over long distance, because you have enough power, right, to do this kind of measurements. And also, because you have enough power, you can actually do frequency conversion, do OPOs, and also dual-com OPOs to get then spectroscopy measurement done at other wavelengths. So with this, I would like to conclude, and I hope I could excite you about these dual-com lasers, and next time you buy an ultra-fast laser, think about it, get two and not just one. Okay, thank you very much.
Hi, beautiful work, thank you. I wanted to ask about the potential of using these with amplified systems then, because I saw in the terahertz measurement you can really split them and manipulate them. What's the potential for integrating them into amplified systems, and what advantages do you lose when you go to lower repetition rates downsampling?
Yeah, I mean, actually, this is also a collaboration that we did, and the paper is also published. It just didn't have the time to talk about it. We did it with amplified systems. And the nice thing is also that you can actually, when you measure something really on a fast time scale, you can change the delta F rep so that you have enough, you know, sampling points, you know, on the scope. And you can then measure, you know, from attosecond, femtosecond to many, many microseconds. So by just changing delta F rep, all you want to do is that you have enough sampling points on the scope, right? And that's why it is important that you can change the delta F rep in your measurement, and that's what we showed in this paper, actually. And I really think, you know, unfortunately, I have to retire in a year. But if you ever have a chance to build up an attosecond beamline, I really think it would be worthwhile to explore dual-com in the attosecond domain, because, you know, I mean, I could give another talk on attosecond measurements, and in attosecond measurements, we are totally limited by signal to noise. You know, we are really always coming in, either we burn the signal, we burn the sample, or then we don't see any signal, and there is always a sweet spot where it just works, right? Because we're just limited by signal to noise, you know, in attosecond measurements. And by doing actually this dual comb, you make it fast. And then, of course, the signal to noise improves substantially. So I would definitely explore that one. I don't know any problems yet, you know, but I think that has a lot of potential to do that with also the attosecond generation.
Sorry, you said it was published? Where can I find it?
The attosecond is not published. That's what you guys have to do now.
No, but
the other one is published. I mean, if you send me an email, I'll send you the paper.
Okay, thank you.
Maybe another fast question?
Thank you very much, beautiful talk. I don't know whether I got it correctly or not, but these two combs are both at the same wavelength.
Yes.
So this pump and probe will be resonant pump and probes. You cannot do something like exciting higher energy and probing lower one.
No.
Right?
I mean, your question is totally justified because, you know, in the dye lasers, you know, we zinc pump dye lasers for those people who are a little bit senior. They remember that, you know, the dual comb has been around, you know, with different spectral content, and that was because people wanted to do pump and probe with different wavelengths, right? But it was always the same repetition rate. So the need for having two equivalent beam mode-low pulse trains coming out of the laser with the same spectral content but different pulse repetition rate, that is really goes back to this equivalent time sampling. I mean, in principle, the first things were done by my professor, Dave Bloom, for electro-optic sampling when he synchronized the pulse repetition rate to a microwave signal and then did equivalent time sampling in the 80s, right? And before that, it goes back to the microwave, right? So, I mean, you know, very often, unfortunately, you know, it's not really a new idea.
Hello. Oops. So it's kind of related to the last question. So what do you think about the frequency comb, but in the XUV X-ray regime? I mean,
that's exactly the attosecond, you know, the high harmonic generation. I definitely think that would be something I would love to do, but I have to retire now, so you guys have to do it. Is because what have been shown, you know, when you come with your, you know, the whole high harmonic generation, you know, was really pushed forward with the Tie-Sapphire laser in terms of the nice high harmonics, right? To get into higher and higher frequency. But now this is shifting now to ytterbium doped laser materials and with external pulse compression in these multipass cell. So it all goes into the ytterbium-based system, few cycle pulse generation with very high quality. And then you can just take these two combs with different repetition rate and generate also the high harmonics with different repetition rate. And then use attosecond spectroscopy with this dual comb configuration, or use the high harmonics with a different repetition rate and the electric field to do this kind of improvements for signal to noise. And because everything rolls off with a 1/f in terms of the noise, the faster you make the measurement, the lower is the noise. So that's the key. And I think that's attosecond science needs to work on optimizing the noise on their source, because otherwise they're always going to be, because we're all working kind of on the same excitation level to even see a signal, right? So we need the next push.
Okay, so let's stop here. Now it's coffee break. Let's thank again.
Thank you very much.
Disculpad, aprovecho para deciros que si queréis uniros al grupo especializado de mujeres en física, que no solo somos mujeres, hay también hombres, tenéis durante esta bienal regalitos de camisetas y bolsitos si queréis uniros al grupo en el stand de la RSEF en el otro edificio, donde está ETH Zúrich. Vale, gracias.